Okay, this video is going to cover chapter 14.4, our wind, jet stream, and Coriolis effect notes. All right, the first thing I want you to do on your diagram right here is I want you to label where it is the coldest and where it is the hottest on the Earth. Alright, so obviously we all know that it is going to be coldest up here and down here near the poles, and we have our warmest or hottest temperatures in the middle near the equator. That is the case, we know, because of the tilt of the Earth and how the sun heats the Earth. It's going to hit the middle portions of the Earth directly, so they're going to receive direct sunlight from the sun, and up here at the poles they're going to receive indirect sunlight, therefore not getting as warm. Now the second question here says to draw what convection currents would look like on Earth if the Earth didn't rotate. So if the Earth just sat still and went around the sun, so it still revolves around the sun, it just doesn't spin, how would that change what things would look like on Earth? Okay, obviously that's never going to happen, but what would happen if that were the case, thinking about convection, we would understand that this cold air up by the poles would sink to the equator, it would be warmed, therefore it would become less dense, and then it would rise back up to the poles where it would get cold again. It would sink back down to the equator, it would get warm again, and you would have a circular cycle from the North Pole to the equator, and you would have a second one in the southern hemisphere doing the same thing, coming up like this and back down and back up. Okay? Obviously that doesn't happen because the Earth is spinning, therefore giving us a lot of other wind patterns. Alright, so let's look at question number 3 here. What causes the wind?
Real wind doesn't come from a fan. No, in nature, wind is caused by the heat from the sun and the rotation of the Earth. That's what makes these intricate patterns of clouds that we see on this photo from space. It works something like this. This is our great big plastic wind box of science. These lights represent the sun. This ice represents the north and south poles. So here's what happens. Energy from the sun heats the land, and the land warms the air over the land. The air molecules get going faster, and they spread farther apart, so they don't weigh as much for the room they take up. So cold air can push the warm air up. That's why we say warm air rises. So look what's happening. The smoke shows us that the air is sinking over the cold poles, flowing over the cities, and then rising over the warm parts. See, it goes around in a great big circle. And that's what happens on the Earth. Now there's one more thing. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions. Wind is wild.
Okay, so the ultimate cause of the wind then is an uneven heating of the Earth's surface. Okay, so the root cause of wind is actually temperature. All right, you have hot areas and you have cold areas. Cold air is very dense, so that creates high pressure, and hot areas are the air is less dense, therefore creating low pressure. So the air is going to always move, just like when you let the air out of a balloon, The air is always going to move from high pressure areas to low pressure areas. So in other words, the wind is always going to blow from areas that are cold to areas that are warmer. Okay, because that's the atmosphere balancing out temperature, and it's balancing out air pressure. All right, the next concept we're going to look at here falls into the world of what is a global wind. Okay, so this is talking about the Coriolis effect.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left. Coriolis effect. An object in motion.
Okay, so the Coriolis effect is kind of an interesting concept. So because the Earth is spinning, of course, that gives the wind a curved path. Okay, in the northern hemisphere, our winds are going to be deflected to the right. So from wherever the point of origin is for our winds, the air is going to be deflected to the right, and in the southern hemisphere, the air is going to be deflected to the left. Okay. Now, obviously, you'd have to kind of remove yourself from the Earth's surface to kind of see that if you could, because obviously when we're on the Earth's surface, we're not going to experience that, but the merry-go-round concept should make sense to you. Okay. Now, the reason the winds curve this direction is because of friction, or what is called drag. So as the air moves across the Earth's surface, the ground beneath the air is moving because the Earth is spinning, and it creates a frictional force called drag, and it pulls the air to the right in the northern hemisphere, and it pulls the air to the left in the southern hemisphere. It's really just a result of friction. It kind of drags the air in those directions. Okay. All right, so if you look at the diagram here, you'll notice that air does move in different directions. So it's not going to tell you that the air always moves in the same exact direction. It just means that the air moves right or left depending on what hemisphere you are in. Okay, so let's talk about how winds are named. Now this concept works whether we're talking about local winds or global winds. Okay, so we're going to look up here in the diagram right in this area, because this is where we live, is in this band right here between 30 degrees north latitude and 60 degrees north latitude. We are located right about actually where it says westerlies. They are called the westerlies because the wind is named from the direction it comes from. So what that tells us is the westerlies blow from the west to the east. So from the west is why they're named the westerlies. Okay. Up here we have what are called the polar easterlies. So these winds blow from east to west. Okay. If you live near the ocean, you would experience a daily phenomenon called sea breeze and land breeze. A sea breeze is when the wind blows from the sea onto land, and of course a land breeze is going to be a wind that blows from land out to sea. Okay, so again, it's named from the direction it comes from. So some days you might hear somebody say we have a north wind. You would then experience a wind that blows from the north to the south. Okay, so that's an important concept for you to remember because we're going to go over that multiple times throughout this meteorology unit. Okay, so that is how winds are named. All right, so let's talk about local winds because obviously these are the ones that influence us on a day-to-day. So local winds are winds that affect the weather, okay, or day-to-day weather. They are caused by temperature differences, just as we learned earlier in the notes here. So hot areas and cold areas, the wind is going to move from cold, high-pressure areas to warm, low-pressure areas. And local winds really aren't affected by climate. You know, climate, the winds that affect climate are more along the lines of your global winds, like the westerlies, the easterlies, and the jet stream, which we're about to learn about. All right, so let's talk about the jet stream here. Okay, we've maybe heard about it. They talk about it on the news a lot. It really influences our weather patterns a great deal.
Weather patterns are caused by temperature differences in the atmosphere. Those lead to pressure differences, which, combined with the rotation of the Earth, force air to move around the globe. We feel this as wind. Jet streams are very strong winds in the high part of the atmosphere, anywhere between 5 to 7 miles up. The speed of this stream can be more than 200 miles an hour. These bands of air are typically thousands of miles long and hundreds of miles wide. In the northern hemisphere, they broadly flow from west to east and shift north to south according to the season. In wintertime, the temperature contrast between cold polar air and warm tropical air is greatest. The jet stream is strongest at this time of year. These boundaries are also where weather fronts generally develop. A low-pressure stream is like a giant funnel of wind spiralling inwards and upwards, forcing warmish air towards the centre and then to rise. As this moist air rises, it condenses to form clouds. Over the North Atlantic, the jet stream typically steers depressions in a west to east direction. A stationary jet stream pattern over the Atlantic will bring frequent depressions to the same region. Sometimes warm air moves further north than normal, or cold polar air moves further south. This can change the prevailing west to east jet stream pattern. This causes the jet stream to buckle, causing depressions to move towards different regions or blocking their movements altogether. Therefore, jet streams can have a fundamental effect on our weather.
Okay, so the jet stream, in short here, is a fast-flowing, narrow air current found in our atmosphere. Okay, it is found at the very top of the first layer of the atmosphere. So just at the top of the troposphere, right before you get to what the next layer is called the stratosphere. Okay, the jet streams blow from west to east in our hemisphere, and essentially they separate that warm southern Gulf air from the northern Canadian cold air. Okay, and they really can fire up a lot of tornadoes and severe thunderstorms in the spring of the year because the temperature differences between the the Canada air and the Gulf air are very extreme. Okay, you should have your note sheet filled out at this time for 14.4.